And then the final part is kind of, it's going to be presenting a Bayesian analysis method that I developed for these transfer reactions that really also allows you to kind of see the limits of this method in specific cases and the need for multiple techniques in order to actually get at some of these rates. Okay, so what is a globular cluster? So if we look at the picture on the right, we see a bunch of stars. However, this very bright spot right here has a whole bunch of stars. So that's 10,000 to 100,000 stars. And a globular cluster is just that collection of all those stars gravitationally bound in a small radius. And so this picture is actually showing us a picture of 47 Took, which is a globular cluster right next to the small Magellanic Cloud. And so these objects are some of the oldest in our galaxy, and because of the amount of stars within them, how old they are, and how they've been relatively isolated from the galaxy around them, they make ideal testing grounds for theories of stellar evolution, galactic evolution, and the chemical composition of them is also of interest. So for about the past 30 or 40 years, for some recent work that I'm going to show, these objects were thought to comprise a single stellar population. And so what this means in astrophysical terms is that in order to describe the observation of all the stars, so what we see in this Hertzsprung-Russell diagram, with the color of the stars being on the x-axis and the luminosity being on the y-axis. So in order to describe the observation that we see here of the distribution of the stars along this diagram, all we need to specify is the initial chemical composition of the cluster and the masses of the initial stars. And so under this assumption, we can make this theoretical prediction with the red line of a single stellar population, where stars that are not in this large main sequence down here, but are more advanced in their evolutionary tract, were simply more massive to begin with. So the stars later in their evolution didn't form at a different time, they were just more massive, burned through their fuel more quickly, and they've ended up on, let's say, the horizontal branch or the red giant branch. And so this is a very successful theory. As you can see, it predicts the observations very well. However, in the 80s, as we started to gain better spectroscopic analysis, we could actually start looking at the individual surface abundances on stars within the cluster. And so on the left is kind of this first sort of observation, one of the earliest observations we had, that there was some sort of inhomogeneity in this, the stars within the cluster. And since then, this sodium and oxygen anticorrelation, so the red points being individual stars within the cluster, and stars within the cluster appear to show an enrichment in sodium and a depletion in oxygen, or no enrichment in sodium and a normal amount of oxygen. So this anticorrelation, since its initial discovery, has been observed in every cluster it's been looked for in. There exist other light elements that have these correlations and anticorrelations. And sort of the question that we want to get at once these observations are in is this a result of the cluster material being inhomogeneous, or is this some other kind of astrophysical phenomenon? And sort of the final piece of evidence of this being some sort of broader astrophysical phenomenon is that with high-resolution photometry, you can actually start picking out individual stars in that main sequence and see that they do not comprise a single stellar population. So again, these are Hertzsprung-Russell diagrams from 47 Took. And now that you can individually resolve these stars so well, you can actually see that there are different tracks through these diagrams, and that these tracks extend all the way up to the horizontal branch. And so this was first discovered in 2007, and since then has really revolutionized how we think about these objects and kind of renewed interest in explaining the observations. And so what this all means is that the current view of what is happening in these clusters is that there's some initial gas cloud of intercluster material with some composition of material. There's a first burst of star formation. There's some unknown polluter candidate in this first population of stars, which enriches in sodium, depletes the oxygen. It then somehow disperses this back into the cluster, and then finally a second population of stars is born. And this is what we see today. And so this is what is kind of happening inside these clusters. And so just kind of revisiting where we started of what is a globular cluster, what it was thought in the past was that this is just a bunch of stars all in a small radius. But with the ubiquity of these abundance anomalies, they become basically the defining features of them. So these globular clusters are astrophysical environments in star clusters that show these variation in light elements and have multiple stellar populations, with the oldest population enriching material in sodium. And that's seen here for a collection of 19 globular clusters, all displaying the sodium-oxygen anticorrelation. So this kind of takes us to where the nuclear physics can come in. So we're interested in these light element variations in the stars. This is a nucleosynthetic process, and it's happening inside the cluster. So we want to know where it's happening and sort of how it's occurring. And so here we go into the second part. So this title isn't grammatical, but it kind of gets at the point I want to, which is we have what is a globular cluster, which is an object that shows the variations between the light elements. And now we're going to ask how is it, or how does it come to be? And pretty early on, not too long after the initial observations of this sodium-oxygen anticorrelation, the nuclear physics was at such a point that we knew that this could only happen from the so-called neon-sodium cycle, which occurs at hydrogen burning between 70 to 80 million Kelvin. And so what this burning process is that it kind of occurs because there's one stable isotope of sodium, so successive proton captures on neon elements beta decay back down to stability, creating more neutron-rich neon isotopes, which then, once we actually arrive over at sodium-23 through neon-22 p gamma, we can either start the cycle over again with a p alpha reaction, or sodium can be taken out of this cycle forever with the p gamma reaction. And so this is the focus of the study that I did, which is to constrain this sodium destroying reaction, the sodium-23 p gamma reaction. And, narrowing down the problem more, where we have the broadest issue, which is this nucleosynthesis within globular clusters, and then we're going down to a specific reaction in this network. Now we need to find a specific energy range that we can study in the lab. And the way that we do this at these low stellar burning temperatures, let's take, for example, 75 million Kelvin here, is we have this till line, which represents the Coulomb barrier between the proton and sodium-23. And then we have the Maxwell-Boltzmann distribution, which is giving the energy distribution of these particles in the stellar plasma. So these two represent probabilities, i.e. the tunneling probability through the Coulomb barrier and the probability of a particle having a given energy. And when you overlap those two, you get a very narrow energy range from 0 to 300 keV in this reaction that we need to study. So it means we need to study resonances that lie within the first 300 keV of the proton threshold for sodium-23 p gamma. And what contributes to this rate beyond just the Coulomb penetration and the Maxwell-Boltzmann distribution is the presence of narrow resonances within this specific peak region. And just in a simplified way of thinking of these resonances is just that there's some probability of the proton being captured given by the proton partial width. Once it's captured, we have an excited state of magnesium-24, which is the compound nucleus. And then there's some probability of decay into alpha particles or de-excitation due to gamma rays. And so all these probabilities are multiplied together in the cross-section. It's dependent on which excited state in the compound nucleus was responsible for the resonance, and these all form the resonance cross-section. And so this is kind of the heart of what we need to study in the lab is these proton partial widths and the energies of the resonances. And taking it back to the astrophysics, because again, we don't want to study stuff that isn't of relevance to the problem we're trying to solve, is that when we fold it back in this nuclear cross-section into the Maxwell-Boltzmann distribution, we find out that the only important factors and the things that we need to constrain in the lab are the spin parity of this resonance given by JR, the proton partial width, the gamma ray partial width, the total width, and then there's an exponential dependence on the energy of this resonance. And turning from that, these resonances lie above 11692 in the sodium-23 plus P system. So this puts us in this excited state range of around 11 to 12 MeV and magnesium-24. And if we turn over that, we put these resonances into a rate calculator. We see that at this red line, which is the peak of the burning temperature that we're interested in, the only resonance that matters is at 138 keV. This dominates the rate for the temperatures of relevance in globular cluster nucleosynthesis. So the purpose of this study that I'm about to present is basically sort of a test case of how reaction rates behave in the presence of a single isolated resonance and what a transfer reaction can actually tell us about this rate. And so just to give an overview of why we're using transfer reactions, again, this Coulomb barrier is dominating at these low energies. So we're only at 138 keV above the proton threshold. And so instead of directly measuring that in the lab by accelerating protons up to 138 keV, we can actually just bring in a high energy beam of helium-3, deposit a proton in, create the same compound nucleus in an excited state, and then detect the outgoing deuterons. And this will tell us indirect information about the state of interest. And then those state properties can be fed back into the resonance calculations, and we can try to offer constraints to this problem. And specifically, for the case of transfer reactions, we have access to the shape of the angular distribution. So we'll get differential cross sections. And those will give us constraints on the spin parity of the resonance. For this, experimentally, we're going to need to measure many angles with relatively small spacing between those angles. And this will allow us to best make out the shape of the angular distribution. The magnitude of this differential cross-section will be related to the proton partial width. And for this, experimentally, we're going to need an absolute scaling for our data. And then finally, the energy is just going to be related to, in the experiment that we did, just the location of the peak in the spectrum. And this really is aided by high resolution so that we know that all of the counts in the peak location is identified with the state of interest. And so we really want as high resolution as possible with all these other constraints. And so the way that we do that in this experiment is magnetic spectroscopy. So this little cartoon here is showing kind of a cross-section of the Enge Split-pole Spectrograph that we used in this experiment. And so we're just using this magnetic field B to bend the deuterons coming out from the helium-3D transfer reaction, bend them so that we separate them based on their charge to momentum to charge ratio. And then once that's done, these differences in energy levels between the excited states of magnesium will be turned into differences of bending radius. And so a position-sensitive detector will basically allow us to access the high resolution that the spectrograph provides, and then also through an energy calibration give us the energy of these states. So what we're going to do is bring in the helium-3 beam, move this giant magnet around, measure these deuterons at several angles, and then calibrate the spectra to identify states and give us the properties we're interested in. And so we did this at Triangle University's nuclear lab. So there's several accelerator facilities at TUNL, and specifically we're using the 10 million volt tandem lab. We use this lab because that's what provides beams to the split-pole spectrograph, seen over here in blue. So this facility is basically focused on hydrogen and helium isotopes as far as beams that you can inject into the tandem. There's also neutron beam lines. And we also have the advantage of this 9090 high resolution beam line, which gives us a very excellently monoenergetic beam to further increase our resolution and the capabilities of the spectrograph. So after transporting our light beams all the way down through these two magnets, they arrive at the Enge spectrograph, which I'm showing here. So the target chamber is around here. And again, in order to measure this reaction at different angles, we physically rotate this magnet around this track down here. And for this experiment that I'm going to start showing work from now, we measured from 3 to 21 degrees in the lab in 2-degree steps with a helium-3 beam of 21 MeV. Additionally, there were a set of 3 sodium bromide targets used over the course of this experiment, and those just basically had the properties of being relatively stable under bombardment. And so this is what you get. So I'm showing the spectrum for the deuterons at 11 degrees on the focal plane of the spectrograph. And so as you can see, the initial data that you get isn't entirely that informative. You can see there's tons of peaks. There's around 60 in the spectrum. And our focal plane detector, of course, gives us information in arbitrary channel units. So this sets us up to where we need to energy calibrate the spectrum. And this is going to give us the energy of the resonance of interest, which again enters the astrophysical rate in an exponential manner. So it's very important that we do this energy calibration correctly. And this is a little bit of a strong statement, but how well do we know the energies of levels above the threshold in magnesium-24? And so when you're going to calibrate, you need to find well-known states in magnesium-24, identify them in your spectrum, and then you can pick out the unknown information. And at the current time, the INSDEF evaluation was last updated 14 years ago. So at the very least, there's a couple of experiments that have happened in the interim that need to be accounted for as far as energies go. Unfortunately, many of the reactions beyond above the proton threshold are actually coming from the neon 20 plus alpha reaction. So these were studied as resonances in this reaction, which means that the excitation energies are a function of the Q value for this reaction. Now, the Q value itself hasn't changed much in 14 years, but there's kind of this rolling amount of errors where the Q value wasn't updated previously, and it kind of just keeps compounding. And so some of these are severely off and need to be updated. Also, if you look at previous spectrograph measurements where all of the other information comes from, these, of course, also had to be calibrated, which means they also use the Q value dependent neon 20 alpha resonances. And they typically had quite a few calibration states and high order fits, which means there could be some lurking systematics in there that aren't exactly clear. There's also another issue with the energy precisions being off because gamma ray energies were fed back in to the fit in kind of a complicated manner. So the precisions need to also be kind of adjusted. And what this means is that we were very careful about any state that we chose above the threshold. So as you see here, we've only picked two at 12260 and 12670. These are the only two unbound states that we used. The rest of these are bound states, and preferentially we picked measurements that had gamma rays, that had known gamma ray energies, and then performed a third order fit. Now the other thing we were careful about was picking states that did not have a known doublet, I guess you could say, within a certain energy range. So if you get a state and a set of states that are separated by about 10 keV, if you pick the wrong one, you're going to throw off your entire calibration process. So as you can see, we didn't necessarily pick the most populated states in this spectrum. We picked the ones that had the least ambiguity in what the assignment was, and we verified this through other methods as well. But for technical details, this arbitrary channel unit is now turned into the bending radius, and then the kinematics will give us the energy. And once we know the energies, we can see that the state of interest, which is going to lie in this window here, around 11 to 12 MeV. So I'm now going to zoom into this green box and show the results of our energies. So these represent the weighted average over the 10 angles studied during this during the course of this study. So if we zoom in, this tiny weakly populated state in red is the state of interest that corresponds to this 138 keV resonance. You can immediately see why the high resolution is necessary, because there's a higher lying state just 30 keV away, as long as some contaminants that wander in and out during the course of rotating the spectrograph. And based on our results, we get a value that's fairly discrepant with the previous value. And so this previous value, which is the most precise measurement of this state to date, was also taken at TUNL using the Enge Split-pole Spectrograph. And so it begs the question why there's a difference between these two measurements. And we think we've narrowed it down to the fact that this state, highlighted in orange, which corresponds to this highly excited peak right here. This is part of or at least there's two states that are known to exist in this region. So there's one that's around 11,315, and there's one around 11,330. The previous study calibrated using this state at 11,330, and this is the final state before the astrophysical region of interest that was used in the calibration. So you pick the state that's 15 keV higher than what the state is, and then that throws off the rest of the energies, is our proposed mechanism for the difference. Now, this isn't terribly interesting in and of itself. It's just the energy of one state. But again, we're doing astrophysical measurements, which means we have exponential dependence on these resonance energies. So using a new recommended energy based on two other measurements in ours, we have this recommended value at 825 now. And that is enough with the known properties of this resonance to shift the rate by a factor of 5, which means the sodium in this proposed burning environment is destroyed at a factor of 5 increased rate. And on the right here, what I'm showing is the reaction rate as a function of temperature, and it's been normalized to its median. So this is just showing the uncertainties that exist from the nuclear inputs. So these are just uncertainty bands around the median rate. And the blue line is the previous rate, and so we can see that the blue rate's uncertainties basically disagree with where the new rate is, and that shows kind of the importance of these kind of energy measurements. But this can't really be the end of it, because again, the two most precise measurements so far are spectrograph measurements, and it would be nice to have some sort of gamma particle coincidence to kind of pin all of this down and have a nice kind of check on these measurements. Okay, and so with that, I'm coming to the last part of the talk, which is probably the most detailed, which is how we go from getting angular distributions measured in the lab to actually putting constraints on the spin parity of this resonance and getting proton partial widths so that we can calculate the rate completely. And so this is, again, a lot more complicated than the energy calibration case. So in the energy calibration case, we're just picking states, fitting a polynomial, and then we're done. Whereas this angular distribution that I'm showing for a bound state with a known spin parity, this is going to require a nuclear reaction theory, and then that nuclear reaction theory is going to introduce additional uncertainties into our calculations and the properties that we extract. And specifically, those proton partial widths that we were interested in are proportional to basically a term that we can calculate from theory called the single particle width, multiplied by the spectroscopic factor c squared s. And so this c squared s is also a relationship, or is related to our experimental data based on a ratio to a calculation from a theory called DWBA, which I will define on the next slide. But once we have this theory, we can calculate from the ratio of the two cross sections the spectroscopic factor. If this theory is able to successfully describe the shape of this angular distribution, that will tell us about the transferred L value. And then additionally, as you can see here on the y-axis, our data isn't established to an absolute scale. So we need the theory to also establish an absolute scale in this case. Okay, and so DWBA stands for the distorted wave Born approximation. And in this case, we're assuming a direct reaction process where a helium-3 particle comes in, transfers a proton, and then a deuteron exits on some nucleus A, and then nucleus B, which is A plus the proton. And so the way we do this is by assuming that this transfer is actually a perturbation on the elastic scattering of the entrance channel, which is the helium-3 plus the sodium-23 in our case, and the exit channel, which is the magnesium-24 and the deuteron. And so these elastic scattering cross-sections are actually generated using optical potentials. And so these optical potentials are basically a way that we can get at simplifying the multinucleon problem in this case. So instead of describing 3 nucleons interacting with 23 nucleons, we're instead talking about one particle traveling through some average potential well. And then in the case of the transfer, this proton is going to be deposited into some single particle state that's with quantum numbers related to the shell model. And just to kind of drive home why this is an issue, I've brought up this kind of mess of equations right here. And this is meant to be a mess because it's meant to show kind of the mess that we're in, which is that in order to describe these elastic scattering cross-sections, you are using phenomenological potentials with fit parameters that are meant to reproduce these cross-sections. So what we're taking is a bunch of Wood-Saxon form factors, and each Wood-Saxon term depends on a potential depth, potential radius, and a potential diffuseness. So it has 3 parameters per Wood-Saxon form factor in here. And then we're combining real parts, imaginary parts, spin orbit parts, and all of these terms are meant to reproduce the elastic scattering that we see in the lab. And so that means at the very least you have 6 free parameters per reaction channel that you're interested in. And in this case, we're going to fit this to our elastic scattering data. And so, of course, there's a lot of potential uncertainty in this case that we need to account for. And that's kind of where we're going for it. And so this is our data. We took it from 15 degrees to 59 degrees in the lab, 5-degree steps. We only measure it for the entrance channel because that is the same beam and the same target as the transfer reaction that we're interested in, so helium-3 beam and the sodium-23 target. This cross-section is going to be used to establish the absolute scale via normalization factor, and then we also wanted to provide constraints on the optical model parameters. Okay, and so the way we're going to do this is using Bayesian inference. Okay, so I've kind of shamelessly stolen this picture, which I did not make, from John Kruchkin's book, which is called Doing Bayesian Analysis. It's also called the puppy book because he uses puppies in the entire book to describe probabilistic concepts. So I will do the same in this case. So Bayesian inference comes down to using Bayes' theorem to describe, the statistical properties of our data. So we want to use this to do the statistics on this elastic scattering cross-section and eventually our transfer cross-sections. And so the way this is done is by just multiplying a bunch of probabilities together. And this relationship is just entirely logical. So it's a logical relationship between these probabilities over here on the right with the 3 puppies and the one on the left. And these each have specific terms, which all kind of make sense once you think about it. So I'll go through them. So the first one here is called the probability, or it can be read as the probability of the data given the model parameters. So in this case, this is the probability of our elastic scattering data and our transfer data given the optical model parameters. And this is equivalent to the likelihood function that you frequently encounter in traditional statistics. That is combined with the probability of our model parameters that we had before we performed the experiment. So if you've heard of Bayesian statistics before, you've probably heard about these prior probabilities and all of the problems associated with them that people typically think of. Over in here, these 2 probabilities are divided by a normalization factor, which is called the evidence. So this is the only pitfall of this picture, is that in the original picture, the puppy is yawning because it doesn't have anything to do with the problem at hand. However, we'll see in a second that this normalization, or also called the evidence, will actually be essential into calculating the probability of a given L transfer for our problem. Okay, so we take all these factors, we combine them together, and that will finally give us the probability of our model parameters given the data. So this will give us a distribution of likely optical model parameters based on what we observed in the lab. And this is called the posterior distribution. And this will also provide us the uncertainty estimates on any parameter that we're interested in. Okay. So, we took the time before this study to test this method on another data set, and we published this paper seen here. And what we wanted to set out in this paper was kind of just a framework that closely follows how these experiments have been done traditionally and kind of intended towards experimentalists. So there's a lot of problems with just fitting elastic scattering cross-sections and then doing a transfer analysis, but that doesn't stop people from doing it. So that means that we also need to kind of fold in all these uncertainties and try to say, if you do this, what is what is the uncertainty associated with the quantities that you derive. So this is really aimed towards kind of an experimental perspective on the issue. And so what we see here is that the Bayesian method breaks down into two distinct quantities that we're interested in, which are also estimated in distinct ways. So we have the traditional case of what's called parameter estimation, where we estimate the probability distribution of the spectroscopic factor, which is going to be dependent on our elastic scattering data, which is informing our optical model parameters, and then the transfer data set. And so that's what we're showing here, is that these bands are the calculated transfer cross-section with some 68% credibility interval. And that's shown for the L equals 3 and L equals 2 transfer. Now, on the other hand, if you calculate the evidence for these two transfers and all of the other likely transfers, so for helium-3D, the most probable transfers are 0 through 3. So we sum up the evidence for 0, 1, 2, 3. That provides us a normalization. And then if you just divide the evidence of a given transfer, so in this case the L equals 2 transfer, you put that evidence over this normalization factor, that gives you a proper probability that you can plug into further calculations. And so I'm showing here that these two lines have associated probabilities of basically 90% and 10%. And the reason that these are distributions is because there's some statistical uncertainty in the method of actually getting this evidence. But in principle, this evidence is just a number. So this is just some simple probability. Okay, and so we can just apply this to the data that we have for sodium-23. And the way that's going to work is that we're going to use Markov chain in Monte Carlo, which I'm not going to go into right now, but this posterior is a very complicated function that we're going to need to estimate somehow. And the way you do that is Markov chain Monte Carlo. Again, the normalization was estimated during the fit. So if we look over here on the left, you'll still see that this is some arbitrary unit over a ratio to Rutherford. And so we have this normalization parameter, but it's still difficult to plot all these things in one kind of typical cross-section plot. But with that caveat, this is what the uncertainty in the optical model parameters does to the fit for the elastic scattering data. So this dark purple band is the 68% credibility interval calculated during the Markov chain. The light purple is the 95% credibility interval. So those roughly correspond to, for a Gaussian, that's like 1 sigma and 2 sigma. So this all seems to work out pretty well, but I've also hid kind of an essential part of doing this analysis, and I think one of the strengths of doing it in a Bayesian way is that you encounter sort of all of the traditional problems that we've had with these phenomenological optical potentials. And so as I showed before, these optical potentials are just a linear combination of Woods-Saxon potentials. And the Woods-Saxon potential itself has a very dramatic correlation between its depth parameter and its radius parameter. And so when we first did the calculations for this elastic scattering data, since we have, we're using this Bayesian approach where your probability distributions go over this entire space of all the model parameters, it actually finds what have historically been called the discrete and continuous ambiguities. So the discrete ambiguities are the fact that we see two of these blobs in this comparison between the depth and the radius. So these two blobs are just all the samples from our calculation, and they each represent like an acceptable solution to our problem. And we can see that it breaks into two modes separated by some amount. And so these two modes produce nearly identical cross-sections for our data. Now the other one is the continuous ambiguity, which I'm showing the analytical approximation that's been known from the literature before. And so this is just a correlation between these two parameters. So these two parameters are correlated, which isn't a big surprise, but it is there, and it's an important thing to factor into our analysis. And so the way that you could potentially solve this just experimentally, though it will still probably be an issue, is that we can see these two different modes produce two different cross-sections at higher angles. So potentially, this is just an artifact of us measuring only up to about 60 degrees in the lab. Now, it's still probably going to be there regardless, but you can severely diminish the effect of it if you measure more angles. For our problem at hand, there's about a 7% change in our inferred normalization depending on which mode we pick, but we're basically going to go with this lower mode here. And the reason we do this is the quote-unquote physical mode that's known from a more extensive global analysis. So it's just kind of an important issue. And the big thing is that for Bayesian analysis of this problem, you have to make a choice about this. And what I mean there is that if you were doing like a chi-square analysis on this data set, you would have your chi-square function and you're just going to maximize it. And so you're going to look at these two blobs, or you're not even going to know about the two blobs necessarily. And so you're just going to pick some starting parameters. You're probably going to pick them close to the global analysis, and then you're going to minimize the problem. And that's going to give you one value, and then through some other method, you'll try to estimate the uncertainties on that value. In the Bayesian framework, again, you're exploring this entire space, so it's always aware of both modes. And so in order to get a single mode, you have to start putting additional constraints on your problem. And in this case, we decided to do that by just saying that we think the physical mode is the one that was identified in the global analysis, and then we just place a basically uniform distribution over this continuous ambiguity. So we just did C, which is the constant associated with it, plus or minus 30%. And so that chops out the higher mode. And revisiting what I showed you before, this is the exact same elastic scattering cross-section, but now I've hopefully illuminated why you can't just pull this out immediately. So this calculation actually takes quite a bit of work to get to. But it's all very enlightening because you're forced to confront these issues that are kind of inherent to your problem. Okay, and so getting to where we want to go, which is again this one state of interest for astrophysics, we can start calculating transfer cross-sections. And so returning to this bound state with a known spin parity, it's described extremely well by an L equals 1 transfer. And we see here that propagating everything through, we again get these credibility intervals in dark purple and light purple. And then furthermore, because we're calculating a transfer, we can get a spectroscopic factor, which is calculated at the same time as all these other parameters. So we're fitting the elastic scattering at the same time that we're fitting the transfer. And so the elastic scattering, the spectroscopic factor is taking all those uncertainties into account. And what I'm showing here on the right is the distribution of the samples for the spectroscopic factor, and those are in light blue. And just extracting like the mean and uncertainty of these, those correspond to the, so if you just take the mean and standard deviation of these, you will get the parameters for log normal distribution. So up here in the right corner, these are not fits to a log normal distribution. These are just the associated parameters of this data set. And the reason that I've put this log normal distribution, which is this dark blue dashed line here, is that the log normal distribution has something called the factor uncertainty, which corresponds very well to our kind of the way we always want to talk about cross-sections or spectroscopic factors, which is plus or minus some percent. So in this case, the factor uncertainty is 1.30, which we would talk about as like roughly a 30% uncertainty in this transfer cross-section. Okay. Now, another wrinkle in this analysis that was interesting to explore in this framework is the fact that the ground state of sodium-23 is 3.5 plus, which means that any state can be formed where it's allowed through angular momentum. States can be formed with a mixture of angular momentum states. And this occurred a lot with all the 2 plus states in our spectrum, which showed something not quite like a pure L equals 0 transfer. I'm just showing the equation here, but basically you can get 2 spectroscopic factors, one for each L transfer. And the question is, does this imply that you get greater uncertainties for each of these components? And the answer to that question is yes. So again, another bound state, 2 plus. This is made from a combination of a 0 plus a 2 transfer, and that is the dark purple. And then the light purple is showing the L equals 0 component. The L equals 2 component in orange is shown here, and you can see that these are quite a bit broader. However, their combination creates a very narrow credibility interval. And if we plug those samples into the same sort of log normal approximation, we see that our factor uncertainty has gone up to 60%. So we've had a dramatic increase in the uncertainty in this cross-section by considering a second component. Okay, so that was just to give some background on all of these methods that we're using. But again, only one state matters. So what we would like to do is just using this method, give probabilities for each of these L values, so 0 through 3. In the past, the only kind of constraints we had would be kind of plugging in direct searches in the upper limits or resonance strength from those searches, combine them with the proton partial widths that you get from the spectroscopic data or the transfer reaction, compare those two, and then kind of rule out which ones don't seem to agree. And that's ruled out 0 and 1 in the past. But it would be nice just to see what the uncertainty in these L values actually does to the rate, since the most recent direct measurement is still below 3 sigma in confidence. So it'd be nice to see basically what is the case if we were just stuck with this spectrograph data. So taking those into account, these are the probabilities of each of the L transfers. So the L equals 0 has something like a 1% probability, and then we have 7%, and then the 2 and the 3 are basically as likely. So we can plug all of those probabilities into our rate calculation, propagate those uncertainties through, and this is what we get here. So this is the same in the blue rate that's known from Luna. And then if we kind of just use our measurement with all of the uncertainties in the L values, our new resonance energy, this is what you get here. And so you have basically a factor of 10 uncertainty in the upper limit, going up into like 95%, you start seeing a factor of 1,000. And this is basically because you have orders of magnitude variation due to the different partial widths that are assumed for L transfers. Finally, getting to the astrophysics, if you calculate the amount of sodium, so this is just some simple network calculation, we can use the Luna rate. They give all of their uncertainties imply this kind of spread of sodium, possible sodium distributions. Just the shift in the resonance energy shifts this peak over. And then if we assume everything of using our proton partial widths, you get this massive distribution and possible amounts of sodium. So, you know, you really need both methods in order to get to good predictions. And so in summary, these chemical signatures are the defining feature of globular clusters. Transfer reactions are basically essential the farther you go towards the proton threshold. So these low-lying resonances really need transfer reactions to inform both spin parities and other things. The destruction of sodium via sodium-23 P gamma, at the very least, has been biased because of the energy calibration issue I talked about before, so the rate is likely 5 times higher. Optical potentials propagate all the way through our reaction theory to ultimately the amount of sodium produced in our network calculations. And these uncertainties can be huge in the very specific case of one isolated resonance with an unknown L value. So with that, I'll finish, and I'll just thank everybody that's helped me, especially the NCSU group. All these people helped me run the experiment, and the UNC group who provided tons of input on everything all the time. So with that, I'm finished, and I'm ready for questions.
All right. Thank you very much, Caleb. Really exciting stuff. So the session is open for questions. So please raise your hand or type your question through chat. So please go ahead. I have many questions actually, but well, let me start. It will give time to other people to chip in. So the spectroscopic factors that you appear to be measuring are rather small. We're talking about 1% or thereabout, right?
Yeah.
So in situations like that, wouldn't you expect some contribution from compound nucleus mechanism? You're doing DWB analysis, right? So direct transfer. What if there is contribution from from compound nucleus?
Yeah, so I mean, as your angular distributions flatten out more, that always becomes sort of an issue, especially for very weakly populated states. So ruling that out completely is very difficult, especially if you don't have, full angular coverage like you need. Um, so that's, I mean, that's what I think the extent of what I would say is that, you never really know too well, but I think the energy we were at, this has a very high Q value, so hopefully that limited those contributions. Um, but yeah, I mean, that's always a possibility.
It's always important to have some estimate of the magnitude that you expect, right? And compare that of magnitude of the cross section and compare it to what you're getting experimentally. So we have the two questions at least, and Daniel Hoff is asking through chat, what was the likelihood function that you used?
So that was just a Gaussian distribution. There's, I didn't get it in too deep to all the technical details. The paper has a lot more information about that. So the basis of it is just a Gaussian function. There's a lot of other parameters that kind of adjust things around, but the core assumption is that the residuals are distributed normally. So
I see. Okay, Udo Schroeder is asking, since you have a deuteron beam available, why not use the N striping reaction? Should be somewhat easier to understand. And how do your optical model parameters compare to the systematics? The previous.
Um, okay, so I'll go in the second part first because I understand that a little bit better. So the optical model parameters, so we had a previous study to compare to, and those come out extremely similar as far as their estimated uncertainties, just using, uh, varying all the potentials and seeing how much everything alters. So that compares pretty well. Older systematics. So I'm not sure if this is directly related to the question, but one of the interesting things that kind of came about from this is that the oldest helium-3 T global optical potential, which I think is, yeah, I'm going to butcher the names if I do it, but it's Pachetti and Greenless. So they had an old potential, and that has an extremely deep imaginary part that can really throw stuff off, it appears, in these studies. So we went to the new optical model from Lang, which came out around 2007 or 9 or something like that. But that's just an interesting note is that potential should be used sparingly, if at all possible. It's been used a lot, but yeah, there's some weird stuff there. So I think this has been, so the
Yeah,
Deuteron beam.
right. So why not to use DN?
Oh, look, I mean, so this is also being intro. Yeah, so we want to detect charged particles. That gives us the best possible resolution. Is the answer I'd have to that. Um,
Okay.
Stripping. Yeah, I mean that's basically it. Is to take it full advantage of the spectrograph.
Okay. So more questions? I don't see any raised. Oh, yeah, Kate. Just a second. So, Kate, you are unmuted now, so please go ahead.
So
Kate? Yeah, here we go.
this was the thorough work you've done in the Bayesian and now. Can you hear me?
Yes, yes, we can hear you.
Slightly.
Yeah.
Okay. I was just going to ask you about your last plot where you were showing sodium abundances, and there was when you included your work, there was suddenly, sorry, we've got terrible weather here, so you may lose me. You may hear the thunder going. You suddenly had this peak at 0, the spike at 0. Should we be concerned about that? Is that meaningful?
Not really. So it's let me go back to the rate contribution or the rate. So as you can see, this is really asymmetric, where there's this like factor of 1,000 on the top here, And this is basically coming from the fact that we assumed that the most probable L transfers were 0 through 3. So the other higher lying L transfers would lead to a lower reaction rate. And so we've kind of cut those out. And the reason this is happening is because the proton partial widths are strongly dependent on the L values. So, uh, there is a factor of 1,000 difference between an L equals 0 transfer and an L equals 3 and the calculated partial widths. So this is just the fact that the rate can go so high that in the kind of model environment I set up, you can just extinguish and burn out all the sodium. And that's just from the nuclear physics. That's not trying to say anything about what we should be concerned about astrophysically. I hope that answers your question.
Okay. We have a question from Tomasi. Could you use a different well-known target to calibrate the Bureau of the Magnetic Rigidity?
Yeah, so we checked first before we established the internal calibration from the sodium. We used an aluminum target, and that was just to kind of initially identify different sodium states that we could use for the internal calibration. That shows the same trends through the region of interest, so that's part of the confidence we have there. There is like a slight difference in the energies that come out, but we found out once we included the difference in target thicknesses and the energy loss that it all agrees very well. So.
I don't know if you've mentioned that already, but which partial width dominates the uncertainty, the proton or the gamma?
So in this case, I mean, everything is made more complicated in this case because the alpha channel is open. But there's one study, one of these oxygen 16 carbon 12 studies that established the gamma gamma over gamma, which indicates that that's close to 1. So in that case, they cancel out, and the resonance reaction rate is just going to be the proton partial width times the spin factors and the resonance energy.
Okay, thank you. We have a question from Augusto. So Augusto, please go ahead.
Yeah, thank you. Very nice talk. Along the lines of Grisha's question earlier, I was more concerned about some effect due to coupled channels because magnesium 24 could, have some rotational effects. And I wonder, I would imagine you could do that in the same approach where instead of running I don't know what you use, DWAC, you can use Chuck or something like that.
Yeah, I mean, again, I would say that there's not anything we did to rule out these possibilities of more, the reaction mechanism being slightly more complex. But just based on what we did observe, so let me just go back to, just these different cross sections, we're basically going after the fact that DWVA seems to explain them fairly well. And there didn't seem to be any portion of the cross section that was indicating that something more complicated was going on. But
well, it turns out that probably the coupled channels may not change too much the angular distribution, but the actual normalization. So
yeah,
that's something you may want to explore, but very nice. Thank you.
Yeah.
Okay. So it looks like we don't have any more questions. So Caleb, thank you very much for this exciting talk and very interesting results. Thank you.
Yeah, thank you. Thank you guys for hosting this.
Thank you for joining this session today, everyone. Goodbye. Bye, everyone.